All right, thank you very much. Thanks for being here till the bitter end. It's a pleasure to be here. I'm going to sort of keep going in this scheme of talks on molecular simulation. So this will sort of also is nicely connected to Francesco's presentation. I'm going to take a slightly different perspective, which I'll motivate in the first few slides. I intend to talk a little bit about priors, but I'll talk a little bit less than I thought I would. I'll talk more about predictive constraints toward the end. But in general, we're interested in sort of putting in some machine learning in molecular simulations. The general philosophy we follow is that we do it very parsimoniously, in that we really try to use machine learning to solve only specific aspects of sort of a whole framework of building and running molecular simulations rather than sort of learning the whole thing. And in this sense, we typically focus on very specific problems, which has two side effects, or two effects. And one is sort of practically, we try to avoid as much as possible extrapolation, and so we try to work or focus on interpolation problems that are reasonable for the machine learning models we have. And sort of more conceptually, maybe it's easier to tell what the machine learning model is doing because we're focusing on very specific properties. And so in general, we're interested in sort of looking at structural property relationships for systems, for material systems in general. And so we're looking at how changing a compound, the chemistry of a compound may affect certain material properties. And so you only sort of have access to forward measurements in the sense that you can take a molecule, can take some material, some chemistry, and then do a measurement, and then that'll take you somewhere and be able to measure some material property, and whatever that is. And you can think of this in many different areas, in condensed matter and soft matter. It's a very agnostic type of picture. And then what we're looking for really are sort of a low-dimensional projection of these quantities here. If you can find this low-dimensional projection, then you'd be able to go backward here, and that you can sort of infer from a certain range of values of these properties what kind of chemistry you want to have. And so this is then useful if you're trying to do some sort of materials discovery or materials design. And the way this has been done traditionally and during these forward measurements has been instrumental in that you're doing sort of maybe cell assays like this at high throughput. And so this is something that's done very often in drug design, where here every little test tube is measuring the exact same thing in the exact same environment, only say changing the compound. So if you're thinking about protein ligand binding, you're always changing the ligand, but always in the same condition, measuring the same property every time. And by this, you're building a library of these forward measurements, and that allows you to sort of later on infer in one way or another, often data-driven ways, try to infer this backward relationship. And so more recently, there's been the prospect of doing this on the computer in terms of like building these databases of how different molecules will have certain properties, running this on the computer instead of having to do this in the lab. And there's different reasons why you may want to do this. One aspect that's been motivated in the workshop is that you don't have to synthesize these compounds, and also which is interesting given the fact that the size of chemical space is extremely large. And so in this context, I want to sort of talk about sort of building force fields and running molecular simulations, not for a specific compound, but for a large number of compounds. And that's been sort of traditionally a little difficult to do because there's been a lot of steps involved in efforts into parameterizing every single compound. And that sort of limits you into going at this in a high throughput way. And so I'll talk about this for two different types of, two different resolutions. The first one is going to be very sort of high level, will sort of, I guess, more directly connect to Francesco's talk right before. And then in the second part, I'll talk about the more coarse-grained resolution, looking at thermodynamic properties and trying to measure these thermodynamic properties to build really databases of free energies. And so the premise here is very similar to what Francesco talked about before, that we're sort of interested in building a mapping, say from properties of the atoms involved, say the nuclear charges and the coordinates, which may be a way to coarse grain your electron density, and then learn a mapping to the potential energy. And then this would allow you to sort of get access to a high-dimensional potential energy surface. And so when doing this, there's different. So this is sort of like the business of building force fields, and there's the main sort of challenge here is transferability. And so there's three large types of transferability you can think of. One is phase transferability, in that how do you go from, say, gas to the condensed phase, and so your model like going across different phases and then transferring well. Conformational transferability in terms of going between different, you're being able to describe a molecule in different parts of conformational space, so say cis and trans isomers here, cis and trans conformations. And then compositional transferability, which has traditionally been the more challenging, is to say, what if I have a molecule and I parameterize this, for this particular molecule, I have a force field for this molecule. What does this parameterization tell me for a neighboring molecule? And so how much can I recycle the force field I have for this molecule and then use it for that one? And that's something that's been traditionally very difficult to do, especially for empirical force fields. And the typical framework is to sort of you have to manually parameterize a force field for every new compound that you have. And of course, in the context of doing some sort of a high throughput study, this is a problem, because you're not going you won't be able to run any sort of high throughput scheme if you have to spend sort of manual time on every single compound you're going to look at. And so if you want to emulate some sort of a high throughput study, you have to be able to completely automate the whole procedure from beginning to end. And that involves sort of this compositional transferability aspect of building force fields. And so the physics-based force fields have sort of been more prominently have made more prominent efforts into going at this to interpolating a potential energy surface, which is really just sort of taking physics-based terms. So these are functional forms that are physically motivated. So for instance, this is a van der Waals interaction. This is the electrostatics. You have some polarization effect here. And then from the physics then you sort of set a functional form for this interaction, and then you have to parameterize this. And this allows you to get very so these types of models can be extremely accurate, but the trouble here is that it typically involves a lot of parameters. You can see here there's a number of terms, and there's a lot of parameters per term. And so if you think about doing this for a number of molecules, then the number of parameters sort of explodes. I sort of like, so Francesco talked a little bit about the amoeba force field, and so these are polarizable force fields. That means that they are classical force fields, but they do have polarization effect, and so this is very different compared to traditional, say, additive force fields that typically don't have explicit polarization effects. And there's a big difference in the amount of physics that's represented between the two, and in terms of a force field parameterization that has a large effects. Because there's more physics here, it's typically a lot easier to parameterize in the sense that the terms better decouple, meaning that the parameters you fit are typically more independent between the different terms, because it's very clean and well defined what parameter is responsible for what interaction is responsible for what. If you remove this term of the polarization, then the physics of your system doesn't change, and so that means that effectively your model that does not explicitly have polarization has to somehow take it into account. And what that means is that you have to sort of take this interaction into effect in some way, and practically what happens is that some sort of polarization effects get hidden into the other interactions. And so what that means practically is that when you're parameterizing force fields, let's say that have less physics, that are more coarse-grained, it's a lot more difficult to cleanly distinguish between what parameter is doing what, and they typically start being responsible for the physics you have sort of neglected. And so the more coarse-grained force fields tend to be more difficult to parameterize. And of course, as we've heard, there's been more recently, say, newer attempts at building force fields, not from a physics-based perspective, but more from a data-driven perspective. You could think of this as really in terms of mathematical potentials, in the sense that you may not know anything about the physics of the system. You're just going to take some reference data and then fit some model. And you may not know any physics, and your model will then sort of will learn a certain amount of it. So these are not physically motivated by default. And so in terms of, and they both have their drawbacks, in the sense that as I just mentioned, these typically have a lot of parameters. When you're thinking about machine learning, then typically the first thing we worry about is that you're going to extrapolate. And so when you're building this for force fields, is also what happens, of course. And so I wanted to show this example, which I've shown in the tutorial already. So I want to show the simple example of extrapolation, or building a small, so trying to learn the Lennard-Jones potential, which is a model for van der Waals interactions. And so the curve is actually here it's in dotted red, so it's here. You cannot actually distinguish it from the blue model, which is a kernel ridge regression model. So it's a very simple machine learning model that's trained on these 20 or so points here in red. I actually showed this at a meeting last week, and Anatol was there, and he made fun of me in public for using 20 points to learn a Lennard-Jones potential. But I have a point here, so give me a second, so you can fit a model, you can fit it very well, it works extremely well, right? And it's completely overkill here, of course, because I'm trying to learn a one-dimensional function, and I have way too many points, of course. But now that I've trained it on these red points, you can see it works really well. I can now extend it to a larger range, and you can see now that you get into trouble in the sense that this blue function now goes to a maximum and then drops down to 0. And it actually drops down exactly to 0 because we have a kernel and we have a uniform prior. And so in the absence of any neighboring training point, you should, from the Gaussian process regression tells you should exactly predict 0. So mathematically, it does exactly the right thing, but physically, it's catastrophic in the sense that it's going to lead you to fuse atoms together at very low energy. And so this will happen with so if you run your simulation long enough, you will cross this barrier. And so this is the exact this sort of things we're trying to avoid when trying to build a machine learning model, of course. And you can see that, of course, even though this is extremely clear here because I'm in 1D, if you're looking at the same thing for a more realistic problem, then these things sort of hit you in high dimensions, and they become really difficult to plot and then sort of scan and visualize. And so to this end, so people have started trying to build force fields that would include a certain amount of physical symmetries, and so this has been mentioned a couple of times in the workshop. So I'm not going to go too much into detail. There's been a number of conservation laws that you have in physical systems that translate into symmetries, and you can try to a priori constrain these symmetries and build a machine learning model that incorporates these a priori. So that means you don't have to learn them, but actually they are satisfied without throwing any data at your machine learning model. There's a number of examples recently from, say, energy conservation, where you can look at, you can think of certain derivatives of your kernel, and Anatol mentioned this yesterday. There's been interesting work in looking at rotational invariance and mostly covariance, building kernels that are covariant. That means that they explicitly encode the rotations in 3D space. And so it means that if you take a sample and you're trying to predict, say, a a vector property, like a dipole moment. And if you rotate the sample, then it's clear that the property should rotate with it. And this is something that you can build a kernel that that automatically sort of satisfies this property, or a subclass of kernels. And what this means in general is that you're reducing your interpolation space because you're taking advantage of a number of symmetries that you have. And so that's helping reduce your interpolation space, and so that's helping sort of alleviate the chances that you are extrapolating. And there's still sort of aspects that are not solved and people are working on in this context in terms of, for instance, long-range interactions. How do you take into account long-range interactions and learn long-range interactions? And given that all of these sort of techniques typically work with a cutoff, and then nothing is taken care of beyond the cutoff, so nothing is learned beyond the cutoff. And also it's clear that you could grow the cutoff, but of course your interpolation space grows enormously with the size of the cutoff. So it's not clear how to take this into account. And you cannot just easily learn the entire potential energy surface as a function of your entire box. Your interpolation space just explodes. And then this aspect of sort of chemical space transferability, in the sense that, for instance, this model is extremely accurate at building potential energy surface or interpolating the potential energy surface from remarkably few coupled cluster calculations, actually. But this is for one specific molecule. And then you wonder, can you recycle this for other molecules? So. Back to the aspect of these intermolecular interactions. So we're interested in learning this mapping. So unlike Francesco's talk, and unlike what my picture might be deceiving, I'm actually not going to be sort of focused on water, but I'm actually interested in sort of learning a sort of intermolecular interactions for a large set of small molecules are made of these atoms, so made of these chemical elements. So I'm trying to be agnostic to the chemistry of my molecule. Which means I'm not looking at being extremely accurate for one particular molecule, but instead I'm trying to get a model that's reasonable across a sort of a neighborhood of chemical space. And here I'm going to look at small organic molecules made of only these chemical elements. And so the route we chose was to sort of try to combine the two aspects of physics-based models and machine learning, in the sense that physics-based models are great at encoding laws and physical laws and symmetries, and things like, if you think of electrostatics, then you know what the asymptotics of electrostatics are, and you don't have to learn this. You don't need to you don't need data to learn what that Coulomb electrostatics is 1 over r. And so physics-based models are great at encoding the physics that we already know. But the one thing that they're missing is that we don't know what even though you may have the asymptotics and how the asymptotics work, you don't have the prefactor. And this is very chemically dependent. And for this, we're using machine learning, which is great at interpolating across chemistry. And so we've seen a number of talks this week that talked about, that demonstrated this. And so we tried to sort of go for a hybrid model between the two. And so the physics-based part is sort of is close in spirit to a lot of, let's say, high-level classical models that exist. It's for the experts. It actually has more physics than something like an amoeba force field, in that we do have things like explicit polarization. We'll have electrostatics in the form of multiple moments. We'll have many-body dispersion. I'll come back to this in a second. And then we'll have some charge penetration to correct for multiple electrostatics, and also some repulsion effects. Physically, it actually helps a lot to distinguish these between long-range and short-range interactions, and that's because again, for the physics, it makes it a lot easier to think about these in terms of two different types of theories, one being perturbation theory here for the long-range part, and Francesco talked about this, and then for the short-range, this is sort of a reasonable model for this is the so-called overlap model, which takes atomic densities and computes integrals for atomic densities, and then uses this to try to compute certain aspects of short-range interactions. And so from the physics, it's great because they work well in their regimes. in their own regimes, but not in the other ones, in the sense that perturbation theory is actually not so great at short range. And so you have to do a lot of corrections. And so you have to sort of marry the two. And so then the strategy is to then use machine learning to predict the coefficients you would need in these different models. For these different interactions. So basically learning the prefactors. And so for instance, yes, I do show this. So thinking about, so multiple moments are used for electrostatics. So this is an extension of, I'll show this, but this is an extension of, say, point charges for Coulomb electrostatics. You have to know what point charges to use. And so this is very chemistry dependent. So we're going to learn that prefactor. And then if you think about things like dispersion and polarization, you need parameters for the polarizability. And so this we're going to learn Hirschfeld ratios here. And then for the short-range interactions, we need to know something about how the atomic densities look like. And so we're going to have to parameterize this in terms of widths and populations. And so as you see, so these three types of sort of atoms and molecules properties then are enough for me to parameterize all these different interactions. Almost. I'll come back to this. So for the electrostatics, then the very basics is to start from Coulomb electrostatics. Then we're actually not going to use this. We're going to expand the electrostatic potential. And so we don't just have partial charges, but we also have things like a dipole moment and a quadrupole moment. And these are interesting because they allow you to describe more anisotropic features of your electrostatic potential, and so you can get more detail. So you can typically more accurately reproduce the electrostatic potential of a molecule. The issue here was that dipoles and quadrupoles are actually, they're not scalar quantities, and so they rotate with the sample. So this is something that I mentioned before with these covariant kernels. So you have to have a way to treat this in the sense that I don't want to have to learn all rotations of a vector or a second-rank tensor. So there's different ways of going about this. I talked a little bit more about this in the tutorial, so I won't go back into that. But basically, it's extremely, so there's a lot of, people talk a lot about rotational invariance when you're talking about learning scalar properties. If you're thinking about learning vector and tensor properties, you have to think about covariant kernels or ways to learn in a covariant way. Because you don't want to have to learn empirically the 3D rotations in 3D space. It's just too expensive. And so here, the way we're doing this is actually with kernel ridge regression. So it's a very simple model. We're using the atomic slalom representation, which I think Anatole mentioned, but I'm not sure don't remember if you went into detail. So these are basically, you have 1, 2, and 3 body terms in your representation. This is basically the nuclear charge. Here you have pairwise distances that are scaled by 1/r⁶, because that's how London dispersion works, or the main term in van der Waals interactions. And then here you have 3 body terms, and these are also, the functional form emulates an Axelrod-Teller-Muto potential, which is a model for 3 body van der Waals interactions. And then what you can see is that we can learn charge, dipole, and quadrupole. So we're showing learning curves here. So what's the error that we generate in our machine learning model as a function of the number of atoms in the training set? There's 4 different curves because I have 4 different types of chemical elements. So I have 1 machine learning model per chemical element. And then each machine learning model then is responsible to describe the multiple moments in any environment of this chemical element. And so what you can see is that, it's a lot easier to learn charges than dipoles and quadrupoles. But it's also easier to learn, say, a hydrogen or an oxygen compared to a nitrogen or an oxygen, a carbon. And one reason for this is that a hydrogen is always a terminal atom, so it has the types of chemical environments it has is a lot simpler. And so it makes sense that this would be a lot simpler to learn than something like a carbon that has more complex valencies. You can also see this when you look at correlation plots of our reference data with the machine learning model. But in general, so you can see that, so we have some outliers, but in general it does actually really well. And so we can actually, for a large number of molecules, so this sort of like simple machine learning model is enough to sort of interpolate across this chemical space of small molecules. For dispersion, so there's different models, of course, to think about and model dispersion effects. The simplest model you can think of is London dispersion, and you can actually very simply derive this, so the 1 over r to the 6, you can very simply derive this if you think about two harmonic oscillator that you get to interact with that you couple and have interact through a dipole interaction. So you get the 1 over 2 to the 6. The advancement from Casimir and Polder through their Casimir-Polder integral was that they could decompose this prefactor, the C6 here, and express it in terms of atomic polarizabilities here. And so you can actually think about this in terms of an atomic polarizability of atom A and an atomic polarizability of atom B. And so this was something that allows you to decompose clearly the contribution of the two atoms. So let's say it's a lot more interpretable than this coefficient C6. Which also tells you that if you have the atomic polarizabilities, actually you have the prefactor for the interaction. And then things like the people have gone beyond in terms of describing many-body dispersion, and so there's different ways of doing this. One approach has been to go through so-called couple fluctuating dipole models, so really just taking quantum harmonic oscillators and couple them. There was an early paper from Alexander Donchev, I think in 2006, and then Alex Tkachenko and co-workers sort of expanded this and described this in terms of atoms and molecules properties, but it's basically the same model. To try to, and it's basically a many-body generalization of the London and Casimir-Polder integral here. And so what it tells you is that if you have these Hirschfeld ratios, then you can compute these many-body dispersion interactions sort of from first principles. And so these Hirschfeld ratios, really without going into detail, are basically the ratio of the atomic polarizability in a molecule divided by the contribution you would have for a free atom, so an atom that's in the gas and not interacting with any other atom. And so it's sort of like it tells you the confinement of the electron density for this particular atom. And so there's different ways. So this then has to do with sort of wave function partitioning methods, and there's different ways of doing this. Hirschfeld ratios are one way of doing this. But basically, the point I want to make is that this is a simple quantity to learn again. And so this is, again, now it's a different machine learning model compared to electrostatics, and its job is to learn these Hirschfeld ratios. And you can see that with a very simple, also simple kernel model, we can reach that. And then for the polarizability, you can then sort of basically compute induced dipole moments by basically having taking your local electrostatic field and then having your different induced dipole moments then interact through a dipole tensor. And this is something you have to solve iteratively, because you can see that these induced dipole moments show up on both sides of the equation. And this is what these explicit polarization models solve. And what's interesting here is that you can actually use also the atomic polarizabilities and these multiple moments I told you about before, and these are the only two inputs you need to solve this. And so when you do this, I should mention all the reference calculations we use are a number of small molecules we calculated from DFT in the gas phase. So these are just single molecules in the gas phase, and that's the only sort of data we're using to build our machine learning models. And then from this, we try to compute the molecular polarizability, and you can see we get very good agreement with respect to experiment. This is our machine learning model. This is from the Tkachenko-Scheffler paper, so this is directly from DFT. You can see that it's virtually identical. These are the anisotropic components of the molecular polarizability, so this becomes a lot more difficult. Actually, and this is against experiments, and actually the DFT and the machine learning model are equally good or equally bad. but there's no, so meaning that at this point we're sort of reaching the limits of the reference data. It's not the machine learning model. And so from this, it's completely non-parametric in the sense that I'm building machine learning models for these sort of prefactors for my different interactions. And there's no free parameter I have. There's a couple hyperparameters, of course, but they're because these are kernels, there are very few hyperparameters, so it's basically parameter free. There are actually, once you sort of put these physics-based terms together, you have to scale them with respect to one another, because sort of there's nothing here that tells you how one interaction scales with respect to the other, so you have to scale them. And these introduce a few sort of adjustable parameters in our force field. Interestingly, we only get 7 of them, and these 7 parameters, there's nothing that indicates that they should depend on the molecules, and so we actually don't make depend on the molecule. And so instead, we have 1 free parameter for polarization, 2 for dispersion, and 4 for the repulsion, 1 per atom type or chemical element, and we sort of freeze them across chemical space. And so we only have 7 parameter fit to do across chemical space. And that's that's very different compared to traditional force fields. We get hundreds or thousands of parameters typically. Here we get 7. And so what we do is that we take a data set of dimers. Here, this is the S22 data set, and put the reference. And for these have, so there's intermolecular energies from coupled cluster data, and so we basically fit these parameters to reproduce as best as we can all these intermolecular energies from coupled cluster. And then from now on, everything I'm going to tell you has no more free parameters. So we've completely frozen our model, and then we're going to use it in the sense that we'll use it for any molecule that we're interested in. We're not going to do any further parameterization. With the machine learning models are fixed, and then these parameters are now frozen. They've been optimized here. So we first looked at the so-called S66 database, which is a database of 66 dimers of organic molecules. The A means that you take these dimers, then you change the angle between them and put them out of equilibrium in terms of meaning that put them out of their ground state. And then you can see here the correlation plot with the reference coupled cluster data, and these are our predictions. And you can see that. So the accuracy is really good, even though, of course, a lot of these molecules are not in our training sets, right? So it picks up parts and bits and pieces from all these atoms and molecules. It picks these different. It makes predictions, and then we get actually very reasonable for these intermolecular energies. We did the same thing for the SSI database, which is a database of amino acid pairs that are found in the PDB, and they were run at coupled cluster level as well. And then again, we get this correlation plot. What's interesting is this one point here that's really high energy. And you can see it because the tyrosine side chain here is very distorted because this side chain comes too close, and you can see it distorts this hydrogen here. And you can see that we actually do really well. So even though this leads to a very high intermolecular energy, and we actually reproduce this remarkably well. Even though, of course, we did not put this particular geometry, this very out of equilibrium geometry in our training set. And so it tells you it's very robust against these types of changes and sort of going out of the ground states of these molecules. And that speaks for the amount of physical interactions we put in there, in the sense that it makes the model very robust, and it helps it not extrapolate too easily. Then we've looked at the same thing for these were amino acid pairs and DNA base pairs. They get a little more difficult, especially because the quadruple moments here, there's a lot of pi stacking, and so the quadruple moments become really important. And so this is where we do a little worse here in some of these, but in general, it's very encouraging. And then one thing we wanted to do is to see to what extent we could really sort of extrapolate in terms of toward the condensed phase. And so here we looked at water clusters, And you can see again that the correlation is very reasonable, given that the only thing it's seen, so the machine learning models have only seen monomers, and then the parameterization of these 7 parameters have seen up to dimers, and that's it. But we still recover the overall trend, even though you'd like to optimize this a little, improve this a little bit. And then same thing for the benzene crystal here, where the excrement. So this is the energy as a function of the expansion, the density of the crystal. Here this is the experimental value, and so in blue there's, I think this is DFT data, and then we're in red here. So you can see that we're a little bit over binding by a few kcal per mole, but we get the right shape, and we get about the minimum at about the right place. So it's promising, but of course it's very challenging to parameterize a model in the gas phase and then have it sort of naturally transfer in the condensed phase. And I think there's still more work to be done to really have this transferability. I think when you look at these different types of parameters, the long range part typically works really well, and so perturbation theory is amazing at long range. The model suffers more from this overlap model. It's not as robust because these are very sort of crude models to look at to model repulsion, and so I think this is where a lot of the shortcomings are showing up. What's interesting is that when the model fails or is not quite as accurate here, it's not random, but it's always a certain type of chemical environment or a certain type of chemical groups that have not been parameterized as accurately as the rest, and so this makes something very systematic in the sense that we clearly realize that there are certain chemical groups that are not as good as the other ones, and so we could go back and reparameterize the models to more accurately parameterize this part of chemical space, and then work again with the model, and this makes which is an aspect of sort of the force field parameterization has been difficult to do in terms of making it systematically improvable without breaking everything else. So in the second part, I'll talk a little bit about so what we do to build to look at more generally at thermodynamics and looking at free energies. And so for this, we've looked at yes?
Sorry, maybe I missed it. Sorry, in your first talk, can you say something about how fast your potentials are compared to other empirical force fields?
Oh yeah, so this is a lot more expensive, right? So because if you think about, so first it's polarizable, like something like an amoeba force field, but the many-body dispersion is actually pretty expensive because it also you also have to diagonalize a matrix, so it's fairly expensive. So we haven't used it to run dynamics yet. But of course, that speaks also for the fact that so you'd want to be able to do the same thing for a coarse grain model, for a cheaper model, say an additive force field. Of course it's more difficult because as I said, the parameters don't transfer as well, and so it's not as easy to say start just from ab initio calculations and then say parameterize a Lennard-Jones and parameterize a partial charge in a force field. People have been trying for a long time to build purely ab initio force field for a condensed phase, and it's not something that's easy to do because you have a lot of these parameters that shift. And this is where things such as learning learning what your conventional force field has not been able to reproduce might be of interest, for instance. So I've been interested in sort of like looking at this idea of again running a high throughput running some sort of high throughput screening, but for a more practical system. So because this is the model I showed you is too expensive, we're interested in the permeability of small molecules. So this is a small molecule, and then you're looking at, this is a lipid membrane. This is a model for a cell membrane. And so you're interested in to what extent, what sort of time scale you can expect if you have a certain concentration of this molecule on one side of this interface, and then see to on what time scale it'll show up on the other one. And this, of course, has some interest in the pharmaceutical sciences, but also from a physical chemistry perspective, it's an interesting problem. It's actually largely been solved in the sense that we know what the reaction coordinate is. It's this reaction, is this coordinate z here, and then you can actually write out the Fokker-Planck or Smoluchowski equation, and that you basically get the answer in that the permeability, which is basically the time scale of the flux of crossing, is this integral over an exponential of this quantity delta G here, and then over a diffusivity term here. And this delta G is the potential mean force, so that's the free energy of crossing this interface. And what that means is that the problem is solved in the sense that if I give you a molecule, and then if you can then just compute this integral, and then you will get the permeability. And of course, that's not practical in the sense that this delta G here, this potential mean force, is not so easy to get, in the sense that you cannot get it from experiments, and you can only get it from computer simulations right now. And it's fairly expensive to get, in the sense that, well, I'll show you in a second. Yes.
Don't you think the D would also have some sort of tensorial properties?
What would have tensorial properties?
Diffusivity.
Oh, yeah. Yes.
I mean, I agree that delta G is hard to get, but to me it would appear the D is even more.
Oh, I see. Yeah. So of course, so you have to parameterize D as well. But there's two arguments here. One is that so it's sort of a log correction compared to the impact of the potential mean force, and the other aspect, sort of empirically, what people have found is that D seems to be sort of very conserved across many different types of small molecules, and so it hasn't been. You can take a crude model for D, sort of fixing it across sort of a large number of molecules, and you get decent results, which you cannot do, of course, for the potential mean force. And so for the potential mean force, one way you would get it is to run enhanced sampling simulation. So this is an example from an atomistic simulation. You'd have the compound here in this lipid membrane around water, and then you could run something like umbrella sampling and then converge the potential mean force. And now this is even though it's a very small system, it's a rigid molecule. It's a one-component lipid membrane. It's something that still takes something like several hundreds of thousands of CPU hours, so you cannot do any sort of high-throughput screening. And this is shown, for instance, in this very impressive paper where they've looked at about 10, 12 molecules, and they computed this potential mean force from atomistic simulations, and it tells you the sort of the amount of computational time they need in order to converge all of these. And it's actually quite a remarkable effort. But it also tells you you're nowhere close to getting a database from this, if 10 is difficult. And so one thing we do is that we run coarse-grained simulations, and that so coarse-graining has been mentioned a few times today. So we coarse-grain in the sense that we replace atoms by sort of chemical groups. So instead of simulating all the atoms, we simulate chemical groups here, and then we only follow the evolution, the dynamical evolution of these chemical groups. And so there's a large history of doing this, and the let's say membrane biophysics community. There's a large number of people interested in using this, or have been using this Martini model. So the way the Martini model works is that it's sort of you take the chemical properties of the atoms embedded within this bead, and you've things such as the net charge, whether there's any hydrogen bond, and then most importantly, what the partitioning coefficients, sort of the thermodynamic properties of this set of atoms. And then from this, you can select, you can assign a bead type, so it's sort of a chemical flavor for these different types of beads. And what's important is that there's only a finite set of these bead types, and so it will become important. So one thing we can do is sort of, so while these are, so first you can sort of assign sort of a heuristically optimize this mapping, so you can try to find define a sort of a loss function in terms of what you would do in terms of converting a molecule in terms of a bead representation. This is mostly taken out of starting from what you would how you would intuitively place beads to roughly reproduce the shape of the molecule. And the other aspect is that while you can just sort of basically stare at these chemical groups and then derive what the charge of hydrogen bonds would be, it's very difficult to do for the partitioning, because that's something that's a free energy quantity, and so this is something you actually have to either know this from experiments, or the way we do it here is that we use a neural network that's trained on the experimental data. So it's directly it's a type of coarse graining that's like what Cecilia showed. It's not based on atomistic simulations. It's really based from experimental data here. And so, but the interesting aspect here is that we can do this sort of automatically and very quickly, and so we've done this for several million molecules by now. And so if you look at this problem, the solid insertion, then you can coarse grain it, and it looks the same. It just looks a little more blurry, but it's the exact same problem. And when we look at the potential of mean force, we reproduce these different types of. You can see that we reproduce the potential of mean force when we compare with atomistic simulations, and this works really well. And it works really well because we feed in this partitioning free energy for each bead. So it's basically taking these partitioning free energies and then looking at it in different complex environments. So this works really well. And the upshot is that we gain about 3 orders of magnitude in time scales here, in simulation time. You can then propagate, you can then compute this probability coefficient I showed you before from the potentials of mean force, and you can see that we get very good correlation with atomistic simulations and also with experiments. So this is something that works well. And that allows us now, it's so cheap that we can actually run this for enough molecules, then start building databases. How much time do I have? 5 minutes, okay. So we've done this so one thing that's interesting is that instead of having to pick compounds you'd have from your fridge, if you're an experimentalist, here what we can do is that we can sort of systematically construct molecules from the universe of these coarse-grained beads. So we start from single bead molecules here, and then there's only 14 of them. Then we can click together 2 beads, and then the combinatorics tells you there's about 100 of them, and it keeps going. And so for these, we go up to about 150 Daltons. So these are still small molecules. If we look at the potential of mean force, so there's 3 different types of environments here: the water, the interface, and the midplane. Here, the interface is between the lipid bilayer and the water. We can define transfer free energies, and then from a thermodynamic cycle, we can close it, and that tells us that we only have 2 independent quantities. And if we plot them, if we plot one against the other, so these few points are from atomistic simulations. There are very few of them because it's very hard to simulate. If we run coarse-grained simulations, you can see that actually there's 2 nice lines that show up, and these are sort of that tells you something about the transfer free energy between these different environments. So something like here the water, this interface environment has something to do which is a bit like an octanol environment, and then the midplane, which is a little bit like an octane environment. And there's some very simple differences in transfer free energy, with simple relationships between them. That allows us to sort of relate this to so it limits the types of potentials of mean force we have, and we have so we can relate this to the color here, which is the water octanol partitioning. And this water octanol partitioning is a bulk experimental quantity, and so this is now something that's interesting because from a bulk experimental quantity, we can now reconstruct this potential of mean force. And we've done this for about 500,000 compounds, which allows us to sort of set now error bars across chemical space. And these error bars could improve them, but they're very competitive. Now we haven't run 500,000 simulations. But the trick is that a lot of these compounds actually coarse grain to the same representation. That's because these are structurally and thermodynamically similar, and so you don't actually have enough resolution to tell them apart. And that has to do with the fact that there's a finite number of B types here. So that makes coarse graining a very interesting aspect when it comes to screening a large number of compounds. Now, to finish, I wanted to. So we've extended this a little bit in terms of going to 3-4 bead molecules. Now we can start getting networks of going in terms of these are compounds on each node, and then each edge here would be a free energy calculation. And then we can run a Monte Carlo simulation in compound space to try to sort of explore the types of compounds that we get, and then do important sampling in, say, a certain free energy of interest. to try to guide us some sort of a very traditional active learning type of thing. And what we can do is that say we've used this to sample in a subset of the chemical space of these compounds, and then we like to predict it for the other set that we haven't simulated because we haven't run it hasn't gone through the Monte Carlo simulations. And so we're using kernel-based machine learning to train on this ensemble, try to predict on that one. It's very simple. So we're using a simple descriptor based on these beads here. And of course, the worry we had is that we'd be extrapolating around outside in this region there. And what we found is that here we get these transfer free energy plots, and these are very reminiscent of what I showed you before. And so these are, so in dark blue we have the data we've sampled from the Monte Carlo simulations, and in light blue we have the machine learning. And you can see that they're sampling distinct areas here, but you can still see that they follow the same trend, the same line here, which is the same thing as here. And the interesting aspect here is that basically we get a constraint in the sense that the thermodynamics tells us that it had to follow this line, and this has to do with this partitioning behavior. And the fact that these predicted compounds, even though we're presumably extrapolating, probably not, the fact that they follow this line here tells you that it's getting the right thermodynamics. And so it's giving you sort of a constraint at the global level of all these compounds we've predicted. And that's an interesting way of being able to tell whether you would want to trust your prediction or not. All right, so I'm at the end. So I wanted to sort of motivate the ways we're trying to use sort of molecular simulations, try to go across chemical space and sort of building force fields across chemical space, not just focusing on specific compound. Of course, the physics encodes none of the interactions here. So this is extremely important to make sure that you're not extrapolating. And then for these high throughput thermodynamics, and the coarse graining actually helps us reduce the size of chemical space, which means that we have fewer simulations to run and allows us to do screening in a very efficient way. So I'd like to thank my group members, especially Roberto, Christian, and Karen, who did a lot of the work here. I'd like to thank the EMI-NOTA program, who funded the second part of the talk, and actually the IPAM, the many particle systems 3 years ago, where I did part of what I told you about in the first part of the talk. Thank you so much.